1, go.
Good afternoon, everyone. Thank you for joining us today as we present to you our final design for a robotic gripper for automatic crab manipulation. I'm Qazi Ashraful Haq, and myself, I have Nibir, Noel, Alawi, and Eric. And together, we are GripTech. Giving you a brief rundown through the agenda we are going to follow today. First of all, I'm going to introduce to you the project. Secondly, I'm going to talk about what we did in our preliminary design stages. And then we're going to talk about our final design in the context of material selection, how we performed our engineering and design analysis, all the stress calculations and the dynamic and kinematic calculations. And then we're going to wrap it up by talking about how we managed the project and concluding remarks. Did you know that occupational crab asthma is actually a life-threatening disease affecting workers who work in production facilities where crabs are sorted? Compounded with the fact that it's not just asthma, but back strains, exhaustion, fatigue, and other physiological problems that carry forward later on in life, this is actually a real problem. Hence, GripTech was approached to automate the process. How do we automate the process? We actually designed a gripper, which will be able to safely grab and release the crabs without damaging them. And the scenario for our project specifically was that there is a conveyor belt carrying half crabs, and the gripper has to be able to safely manipulate those half crabs. So now, why are we making it? Why not just go get it from the market? The thing is, industry grippers actually exist, but they're not tailored specifically for gripping crabs. So this design will be the first of its class ever to be made only for crabs. So the challenges are obviously unavailability, and also when you compare this gripper against the specialized specifications and constraints that we have put into our design, you'll see that it doesn't meet most of them. Our design will be able to manipulate the shape of the crab, the complex size of it, the varying weights of different crabs. The design will be made in such a way that it will be able to open and close without damaging the crabs. Also, the budget will be very low compared to this robotic gripper, which is in the cost of $20,000. So our one will be 20 times better, as you will later see. The material will be food grade. Forces and power generation won't be so high that the crab will be crushed, and it will be able to be compatible to be mounted onto an industry or standard robotic arm. Before we dive into the final design, I'll tell you what we did on our preliminary stages. We brainstormed and screened lots of ideas and chose the best idea. We brainstormed to figure out what the best actuation mechanism is going to be, and we identified the major components for our gripper. The material selection was done to choose the best food grade material for construction. Also, we did a motion study to make sure that our gripper is actually feasible. So going forth, Alawi will take on from here to talk about detailed evaluation of our final design and a proof of concept.
Thank you, Qazi. As Qazi has mentioned earlier, there are no grippers that are available in the market to manipulate crabs. However, standard robotic arms are already available in the market. This is where our team came in to deliver a product that is able to manipulate a snow crab. If you closely look at our product, it slightly resembles a hair clip. Please keep the word hair clip in mind for now. During our concept generation, we came up with the following design options: gripper with suction cup, 2-finger gripper with soft pads, 3-finger gripper with motorized mechanism, hair clip gripper, push and scoop mechanism gripper. After screening and scoring these 5 options, we found out that hair clip had the highest score. Therefore, we proceeded with a hair clip gripper mechanism. Now, to understand how our product works, we broke the components into 4 main parts. The first one is mounting frame, slider crank mechanism, gripping mechanism, and pneumatic piston. Basically, the mounting bracket provides a support connection to a standard industrial robotic arm. It also supports our pneumatic piston and holds it in place. This is where the mounting bracket is attached to our slider crank mechanism. The purpose of our slider crank mechanism is to transmit motion generated by the pneumatic piston to the gripping mechanism. Basically, the gripping mechanism is where our snow crab is going to be held and released. If you look at the close of our gripping mechanism, it is designed such that it has enough spacing to accommodate the leg sizes to hold the snow crab in place. For the pneumatic piston, it is an off-shelf component, therefore it requires appropriate sizing and selection. Now to do this, we have looked at 5 main factors. First, a force of 68 newtons is required. Eric will talk more about forces. We need a double acting actuation since we need both push and pull. Material of stainless steel 316. Nibiru is going to talk more about materials. A food-friendly lubricant. Now, to automate this pneumatic piston, we have suggested the use of 3-way solenoid valve. This is how it's going to be connected with the PLC. Let us put all these components together and see how the holding, how the closing and opening is achieved to manipulate our snow crab. If you look at the side here, we have our bills of materials. Nibiru is going to take it from here to discuss more about material selection.
Thanks, Alawi. So from our previous presentation, we have selected stainless steel 316 as our final material because of its food friendly, non-reactive, and its high applicability in food industry. Since we believe in sustainable design, so we wanted to see how our selected material has an impact on the environment, and we found some key properties. Stainless steel 316 can be 95% to 100% recyclable. It has high lifetime and it has low maintenance, which means there is a significant reduction in energy consumption, emissions, and carbon footprint, and hence our selected material has a positive impact on the environment.
Thank you, Nibiru. Before building our gripper mechanism, we needed to first prove it was feasible. We did this with a mobility and kinematics analysis. As shown here, here is the mobility analysis. As you can see, the gripper has 10 linkages and 13 joints. And using Kirchhoff's mobility equation, we were able to figure out that it has a mobility of 1, which makes sense given that we chose this design based on its simplicity. Onwards to the kinematics analysis. In our mechanism, we have 4 loops, loop ABC, CBD, and the gripping claw loops 3 and 4, shown here. So here's an example of loop 3 and 4. Here are the kinematic equations as for position, velocity, and acceleration. The input will come from the slider crank, which is connected to the air piston, and then the outputs would be the gripper link position and the follower link, shown for the opening and closing of mechanism. Next, we completed our preliminary static analysis to figure out the forces required by the piston to hold the crab. To do this, we wrote down the components into FPDs, and we took the sum of the forces in the X and Y directions, as well as the moments around the specified point. All in all, we ended up with 24 equations and 24 unknowns, and we solved it in Excel using basic matrix algebra. And here are our results. For just the weight of the crab, we require a force of 6 newtons from the piston to hold it static. We also simulated the motion of the robotic arm going upwards at an acceleration of 1g. This doubles the forces, and we require 12 to 13 newtons. We'd expect these numbers to actually be lower because we hadn't included friction in the model, and friction opposes motion. I'll now hand it on to Uche, who will talk about dynamic analysis.
We did an analysis of our model to understand the physical behavior using SolidWorks. Now, for the motion study, which was the dynamics analysis, we set the piston to oscillate some distances to see how the opening and closing of the gripper worked. As you can see here, as the forces was added, it needed a force of 8 newtons to overcome friction, after which the forces kept on increasing during the closing of the gripper. And opening of the gripper, the forces started reducing down up to about 8 newtons again. So in total, the gripper closes and opens in 1 second with a maximum closing force of 68 newtons and a closing and an opening force of 60 newtons. As you can see in this graph here, this is the the distance of opening and closing of the gripper, and the maximum open distance is about 18 centimeters. The red and green line represent the clearance, the maximum and minimum clearance of the crab, which is well within this graph. So our gripper will be able to accommodate the different sizes of crabs. So in summary, we have a piston stroke of 23 millimeters, which causes the slider crank to move linearly 35 millimeters, and at the end, the gripper opens a maximum distance of 180 millimeters. Moving over to the stress analysis, we subjected the model to forces loading of 68 newtons from the piston and 10 newtons from the crab. The maximum stress, internal stress acting on the system was 38,000 kilopascals. Using stainless steel as the material, the yield strength is about 172 kilopascals, which is much more higher than the maximum stress, internal stress, experienced by the model. With this, we can see that the model will not yield under this loading. We went forward to look at the deflection of the model under this loading as well. And as you can see above here, the mounting bracket had a maximum deflection of 0.044 millimeters. Now, we expect this to happen because if the model is rigid, then the forces will cause the deflection forces could cause the model to break in the weakest link. But allowing the deflection here, the forces can be transferred to another part of the body which would not break, and the model is stable. Finally, we look at the factor of safety to determine how safe our design is. The factor of safety distribution for the model is 4.5, and what this means is except our model is subjected to 4.5 times the force of the loading, it will not break.
Thanks, Eric. So our project management plan comprised of project cost and Gantt chart. So for our project cost, our budgeted cost for the prototype was $500, and we are successfully able to finish our prototype with just around $150. And for the budgeted cost of our actual paper was $2,000. So what we did, once we did our SolidWorks model of our actual gripper, we brought that SolidWorks model to the tech service at Memorial University, and they provide us a quotation. And since we have to buy pneumatic cylinder as well as the other related components, so we had to add those prices as well. All in all, our final price of the actual gripper was around $1,000, which is almost half as our budgeted cost. And our Gantt chart has these following criteria. Now, once we have proved through engineering analysis that our design is feasible, we decided to pursue our design ideas into reality. And so we built a prototype. So as you can see, this is how our prototype looks like. This mounting frame will be acted as a robotic arm here. And our prototype has also the same mechanism as the actual gripper. And the next image you can see is our prototype holding a crab. So in this next slide, I'm going to demonstrate a video of how our prototype is going to work actually. So you see this series will be acted as a pneumatic cylinder or hydraulic cylinder, you can say. So when the force is applied, it causes the whole lever to open and close. So this is a video without crab, and this is a video with a crab to show that our gripper can actually successfully hold the crab. As you can see, it's moving. And now we'll remove the video parts to show you back that our gripper can successfully able to hold the crab. Can I do it? So once we did our engineering analysis successfully and build our prototype and showed you guys that it actually works. So our next step should be able to fabricate a real actual gripper and test it in a crab processing plant. On behalf of my team, I would like to thank Memorial University, Dr. Luke Rowland, Empowered Homes for their help, and I would also like to thank CSME for hosting this event. Thanks. We welcome any questions.